Good afternoon to all of you joining us today in Timber Design Society's 7th webinar of Series 2022. My name is Namir Amsu, member of the Timber Design Society Management Committee. This webinar is kindly sponsored by the following organizations. TDS committee expresses to thank and appreciate these sponsors for their funding to its activities. XLAM, Simpson Strong Tie, MiTek, and Future Build LVL. Today's webinar is a presentation by Daniel Wellington of MiTek about MiTek lateral solutions, MiTek lateral solutions for multi-story timber buildings. And Daniel is currently working with MiTek New Zealand as a structural timber timber engineer. He engages with lots of technical segments of the building supply chain to help facilitate better building. That's a very short brief which I can read for Daniel's brief. Please post secured very, very soon. Now, having said all of that, I would like to thank once again all the attendees today, and I would like to pass on to Daniel for his talk. Daniel, thank you very much.
Thanks for that, Namir. I'm just going to start my presentation. There we go. Okay. Here. Okay, thanks everyone for joining us today. It sounds like we have quite a few interesting webinars happening over the next few months. Definitely interested for that seismic performance of SIPS panels. That's definitely going to be something I attend to. But thanks for joining us today for another edition to the Timber Design Society's webinar series, part 7. Brings you MiTek's lateral solutions for multi-story timber buildings. If you're just now joining us, my name is Daniel Wellington, as Namir introduced, and I'm one of the engineers at MiTek, and let's just jump right into it. So today's presentation will cover continuous rod systems, namely the MiTek's Z4 continuous tie-down systems. The why, the what, the how, and the where will be covered in today's talk. So I've been advised to keep this presentation fairly untechnical, and indicated to me is that you're likely munching away at some food with this playing on the side. So to keep you from choking on your food, I'm going to try to keep this at a fairly conceptual level and focus more on answering the fundamental questions that engineers usually have when presented with a system like this. So today's presentation will go over the basis for choosing a continuous rod system, differential movement between the structural and the timber and the steel elements, how loads travel within the chords of the shear wall and within the tie-down system. We have dynamic response of the system, failure mode. Then we talk about hidden advantages, guide to specification, and of course we'll finish everything with deliverables. So what you end up with on paper and what you end up with on site. So this goes without saying, but we will mainly be focusing on multi-story timber structures as indicated in the title of this presentation, and the fact that this is hosted by the Timber Design Society. Okay, so let's take the simple timber frame shear wall as an example of how our forces develop. So we have this 4-story shear wall with some base shears, which can be calculated using 1170.5. Then we have this, the base shears can then be proportioned to the floor at each level of your structure, depending on the weight and height of your structure. So we pull that equation from 1170.5, that's section 6.2.1.3, and that's basically going to allow us to determine the lateral forces that are acting at the floor at each level of our structure. So all we do is plug in our base shears into the V of that equation that you see, and the W and the H are the seismic weight and the height for each level. And this leaves us with the lateral force at each level. So if you look at this distribution of the lateral forces, you'll actually notice that V4 is, I'm going to turn on my laser pointer, but the V4 is actually slightly smaller than V3, and that's because the seismic weight of V4 is going to be a little bit less than, the seismic weight of the roof is going to be a little bit less than the floor at V3. So that's why it's like that. So obviously these lateral forces are going to cause overturning moments at each level. The overturning moments can then be resolved into a couple of tension and compression forces. And I know that the tension and compression forces can have different values, but in this case, let's just keep it the same for simplicity's sake. So if we're looking to determine the cumulative tension at level 3, for example, so that would be T3 over here. So T3 would be the moments caused by the lateral force V4 and the lateral force V3. So V4 acts at a distance of H4 plus H3, V3 acts at a distance of H3. So if you add those two moments together and divide by the length of the base, what you have is the cumulative tension at level 3. Yeah, so note that there's a distinction. I keep saying cumulative tension, and there's a distinction between cumulative tension and level tension, which I will dive into later. So, but it is important to distinguish between the two tensions, because the cumulative tension will act on some components of the system, and the level tension is going to act on other components of the system. But there's no need to worry about that at this stage. We'll talk about all of that in just a second. So now that we know where the tension comes from, let's look at a typical approach that engineers normally use when tying down the tension. Okay, so we have our plywood sheathed shear wall, and from the conversations that I have with engineers, it appears that most opt for shear walls like this, with timber studs at the chords to take care of the tension and the compression. So typically engineers adopt the capacity-based approach, which designates a ductile fuse, and as a result requires the surrounding structural elements to be over-strengthened. So in this simple diagram that you see here, the nails fixing the plywood to the shear wall, to the timber frame, are designated as the ductile fuse. And that leaves the plywood, the framing, the chords, and the fixings to all be designed with what is called an overstrength factor. So the principle behind the capacity-based approach is that you are ensuring that the ductile fuse is the first one to blow. And as a result, you have to make sure that the surrounding structural elements definitely don't fail before the ductile fuse. And the approach that engineers normally take is that that you apply an overstrength factor to all the surrounding elements. And typically that figure is something like 2. And as shown above, the tension is transferred through the studs by means of some sort of steel bracketry, maybe like a jib handy brack or something like that. But let's take a closer look at what that might actually look like. So we have some built up studs, some floor framing, and then some more built up studs in the lower level, which and what you might see in most cases, maybe 1 or 2 more studs at the lower level, which might make the fixings a little bit trickier to detail, as the load path is no longer straightforward, which is just another thing to keep in mind. And usually a set of steel brackets are fixed. Usually a set of steel brackets are fixed using screws, nails, or bolts. Then there's a continuous fastener that goes that goes from one level to the next, and that's usually there to transfer the tension from the floor above to the one below. But the problem is, with the tension that is developing as you go down the structure, the fixing's capacity will grow proportionally. So you will likely see several fixing details with bigger capacity fixings at the lower levels and smaller capacity fixings at the higher levels. And now this isn't an issue in and of itself, and it's sort of par for the course, but this can become cumbersome to detail, install, and inspect. Not that you're going to be doing any of the installation, but someone's got to do it. And the last thing you really want is any mix-ups to occur. There's also the matter of horizontal drift. And when we're dealing with timber frame shear walls, engineers typically calculate for these types of horizontal deflection. And there's mainly 4 of them. I think there's 6 actually, but mostly these 4. So that's the flexural deformation, shear, deformation, fastener, slip, deformation, and of course, anchorage, rotation. And herein lies the most important point that I want to make, and that is that when we've got studs and brackets, one of the largest contributors to the horizontal drift is the rotation of the shear wall at the anchorage. Now, this issue is further amplified as we increase the number of stories of our timber building, because that is just going to accumulate. So now if it sounds like I'm trashing studs and brackets, that is by no means true, because they absolutely have their place as a tried and tested tension hold down system. Rather, what I'm doing is offering an alternative that is advantageous when working with more stories. Now, what does more stories mean? I reckon something like 3 plus, greater than or equal to 3. So let's have a look at what that advantageous alternative actually looks like. So a continuous rod system, there we go. And namely the Z4 continuous tie down system. So all that teasing, and now we finally made it to the subject matter. So let's have a closer look at it. So here's what the system looks like on site. So here are the components of the Z4 system. So the biggest component in the system is, of course, as the name implies, the all threaded rod, and that's because it's covered in thread, so it's all threaded. And the all threaded rod is just a steel rod with imperial thread. So I think that's called UNC thread, which is Unified Course National. So no, the system won't work with any metric components. If that's what you were wondering, you can't swap out any of these components with metric components, and it won't function. We have couplers that act to tie our rods together. It's essentially just a rod splice. Then we have bearing plate washers, and bearing plate washer is just a steel plate with a hole in it. And its sole function is to distribute the perpendicular to grain loading on the bottom or top plate. That's all it's there to do. And most importantly, there is, of course, the omega nut, which sets the Z4 system apart from the basic steel tie-down rods, as it allows the system to compensate shrinkage. But more info on that in just a few more slides. And this is one of the things I really want to highlight, as engineers seem to overcomplicate the system, and I want to reiterate that it's really not that complex. So if we just remove the omega nut, like magic, and have a look at what we have something here that is one of the most common things that you see in all of structural engineering, and that is a steel rod. And that's really how you should think of the system. It's simply a continuous steel tension rod with shrinkage compensation. And shrinkage compensation is very important, and it becomes increasingly important when we're working with timber structure. So let me just put that back on there. And let's have a look at why shrinkage compensation is actually important. So differential movement. So now that we've touched on Z4, let's look at why shrinkage compensation is actually important. There are several contributors to downward vertical deformation of your timber building. And here they are. So we have shrinkage, we have settlement, we have deformation, we have creep. And we have shrinkage, number 1. So now shrinkage is simply the dimensional instability of timber with respect to fluctuations in moisture content. So less moisture means smaller cross-section, more moisture means bigger cross-section. I know it's more scientific than that, but let's just keep it that simple at this level. So this phenomenon mainly affects timber's perpendicular to grain dimensions and not so much the parallel to grain dimensions. So if you're trying to determine the vertical movement of your building, you really want to focus on the junction where the stories meet. So let me just highlight that. So this is what's called the zone of movement. And so this is where your stories meet. So you have your bottom plate, you got your floor framing, and then you have your top plate, your double top plate, or maybe your top plate packer and your top plate. And that's called a zone of movement. So if you've got a platform style framing detail that that looks something like this, you can estimate the movement due to shrinkage to be something like 7 millimeters per floor. However, if you opt for a balloon style framing, which essentially eliminates the floor framing part of things, and all you're left with is a bottom plate, a top plate, and a top plate, you've gotten rid of the floor framing, which reduces the zone of movement by about 70%. And what that's going to do is take your shrinkage down from 7 millimeters, maybe down to about 2.5 millimeters per floor. And as a result of this, timber shrinkage is now our #1 contributor to our vertical movement. And it kind of depends on whether you're going with platform framing or balloon framing. That's just shrinkage. Then we have settlement. Now, settlement is the movement your building undergoes as a result of small gaps between studs and plates, and your studs and other similar framing. So it's essentially just those gaps closing up, because we know that in construction, or especially in timber construction, no joint is perfect. So the studs, for example, touching on the top plate are not going to be perfectly miter, and obviously that it's not going to be perfectly square either. So as a result of that, when the building is closed up over time and as the dead load accumulates, those gaps will close up, and it causes a movement in your building that's known as settlement. And this is kind of a tricky one to estimate, as it falls into the realm of engineering wizardry. And what we are left with is an estimate that most people seem to agree with, and that's something like 3 millimeters per floor. So you got to add that into your vertical movement as well. So elastic deformation can be easily calculated. You would need to calculate the elastic deformation of your members perpendicular to grain and the elastic deformation parallel to grain, because remember that timber is anisotropic. So your studs will experience elastic deformation different to your plates, because And a good reference material that I borrowed this equation from is actually Brands' Light Timber Frame guide. So that's always a good reference material that I like looking through every once in a while. And then we have creep. And creep can be also easily calculated, because all you do is grab your elastic deformations and you apply a multiplier to it. And that is essentially what that J2 constant is. And in most cases, engineers just go for like a factor of 2 or something like that. So you grab your elastic deformation, multiply it by 2, and that's your creep deformation. So equation is again courtesy of the Brands Light Timber Frame guide. So again, that's a good reference material. Okay, so adding all this up, you could end up with a vertical movement in the realm of maybe 7 or maybe 10 millimeters per level, depending on what kind of detailing you go for your floor-to-floor junctions. So if you've got a continuous rod system sitting in your vertically moving timber building, your rod will start experiencing compression. In fact, it's not too difficult to estimate the compressive stress on your rod using the 10 millimeter strain and the Young's modulus of the steel. So in any case, it's the compression that's not welcome, as compression is the last thing you want in your tension rod. It's a tension rod. So it's easy to imagine what might occur during a seismic event if the slack in your rod needed to first be overcome prior to it assuming its service load. So we need to allow for the timber building to move freely while the tension rod stays tight or taut. Okay, so what I've alluded to is the need for a shrinkage compensating device of some sort, and that is exactly what we looked at earlier in the presentation. So our omega nut is just that, as it allows, as it's a ratcheting device that allows the timber frame to move downward freely, but not upward. We call it the omega nut. So the previous design was called the cinch nut, and that's likely the name you'll come across when you look through our technical literature. But rest assured, the function is exactly the same, and it's governed by exactly the same capacities. So it's almost, you could consider it a cosmetic upgrade. And here's what the previous design looked like. So instead of having a continuous cap covering the casing of the nut, we used to have a plate that was screwed in at the top. So let me just go back to what we had there. And so the omega nut sits on the floor at each level, So the each floor's vertical movement is compensated for. And here's a simple elevation of the chord of a shear wall showing what we call a run. And a run is basically just the name of all the Z4 components from top to bottom. So you'd have the, the omega nut, the bearing plate washer, the rod at that level, so on and so forth for each level. And that's what comprises a run. Of course, you would see exactly the same run mirrored over on the other end of the shear wall. There are omega nut sizes for all of our rod diameters, and this helps us specify the tie down system quite easily. And yeah, and there's what I believe to be a simple design philosophy when it comes to Z4 component specification. So now what I want to highlight is this last point that I'm making, which is simple design philosophy. But in order to understand this, we must first understand the failure mode of the omega nut. So let's start with how tension is developed within the system, within the tie down system. So, okay, remember when we had a look at the horizontal forces at each level, the lateral forces at each level, and derived the cumulative tension? And I mentioned that there is such a thing as the level tension and the cumulative tension, and that the cumulative tension affects some components and the level tension affects the other components. So let's have a look at what that difference really looks like. So let's start with the level, with what the level tension looks like in a physical sense. So let's first imagine our shear wall that I introduced a few slides ago. And let's say that there is no tension tie down between the levels. If we take this untied down structure and apply some base shears to it, since the chords aren't joined together, the tension generated in the chord at each level is irrespective of the tension in the chords above or below. We refer to this tension as the level tension. So let me read that for you again. Since the chords are not joined together, the tension generated in the chord at each level is irrespective of the tension in the chords above or below. We refer to this tension as the level tension. What does the level tension look like mathematically? Let's have a look. Okay, so let's revisit the cumulative tension at level 3. So T3 is over here. So we're trying to derive the cumulative tension using this here. So we just have the moments created by these two lateral forces, V4 and V3. Divide that by the length of the base, and you've got yourself the cumulative tension at level 3. You expand that equation, and you've got these three terms. You reorganize those three terms, and you've got something like this. You're left with these two terms. 1, 2. And what we find is that you have the level tension at level 3 is the first term, and the level tension at level 4 is the second term. It may not make a whole lot of sense just yet, but if we perform this exact same exercise on the cumulative tension at level 2, it starts to make even more sense. So let's look at T2. So that's the cumulative tension at level 2. So T2 is caused by the overturning moments caused by the lateral force V4, V3, and V2. So V4 is acting at a distance of H4 plus H3 plus H2. V3 is acting at a distance of H3 plus H2, and V2 is acting at a distance of H2. Divide all that by the length of the base, and you've got the cumulative tension at level 2. You expand out that equation, and you've got these few terms. You reorganize it, and you've got these three terms. And what that is the first term is the level tension at level 2. The second term is the level tension at level 3. And the third term is the level tension at level 4. But the last two terms should look a little familiar, as they are exactly the same two terms we saw earlier in T3. So you could say that T2 is just the level tension at level 2 plus the cumulative tension at level 3. So hopefully that makes sense. You could also say that the cumulative tension at level 2, T2, is equal to the level tension at level 2 plus the level tension at level 3 plus the level tension at level 4. Or you could say level tension at level 2 plus the cumulative tension at level 3. And now that should make more sense intuitively as well as now mathematically. Okay, so now while we're focusing on the tension at level 2, let's take a closer look at how our level tensions are actually traveling within the timber and the rod system. So the level tension is going to try and lift up the floor, pushing up on the studs and the floor above through the bearing plate washer and engage the omega nut, creating tension in the rod below. So in the diagram above, or the diagram that you see over here, the level tension at level 2, that's delta T2, is pushing up the floor at level 2, pushing up the studs and pushing up the studs at level 2 and the floor at level 3, pushing up on the bearing plate washer at level 3 and engaging the omega nut at level 3, adding delta T2 tension to the rod at level 2. But keep in mind that the rod, because it's continuous, is also being pulled on by delta T3 at level 3 and even delta T4 at level 4. So since the rod is continuous, it experiences the cumulative tension at a level, and we must therefore use the cumulative tension at a level to design the rod at that level. But the bearing plate washer and the omega nut only experience the level tensions, and we therefore use the level tensions as the demand to design those two components. So in summary, use the cumulative tension to design the rod and the level tension on the bearing plate washer and the omega nut. And that's what the two tensions are and what they're doing within the continuous rod system. So hopefully that makes sense. We're doing good for time. So that being said, one must ask the question, what exactly is the capacity of the omega nut? To answer that question, we have to ask ourselves another question. Is there a governing standard for shrinkage compensating devices? The answer to that question may actually surprise you, but yeah, there is what is known as an acceptance criteria for shrinkage compensating devices, because believe it or not, there are a few types of these. I think there are 3. Compression controlled shrinkage compensating devices, tension controlled shrinkage compensating coupling devices, and tension controlled shrinkage compensating devices. Without going into too much detail, the omega nut is just a tension controlled shrinkage compensating device. It's the latter of the 3. So we refer to the acceptance criteria document AC 316, which standardizes the testing, the design, and the performance of the shrinkage compensating devices. And it's a document published by the International Code Council, the evaluation service that they have. So it's available to download from their website, although it is far from free. Yeah. So testing. The test is essentially a static tension test where we impose a load on the omega nut to see when it fails. Illustrated above is a schematic of what the test rig looks like or looked like. AC 316 gives us specific instructions for how the testing should be carried out. There are 3 phases to the testing, where the deflection due to slip is recorded in the initial phase. So we have so the first phase records the slip of the omega nut. Then phase 2 includes taking deflection measurements at the rod's capacity. And the reason these 2 deflection figures are important is because the deformation due to slip and the deflection at maximum rod capacity becomes important when we're calculating the deformation of the Z4 system under earthquake tension. So I'll show you later with an example of how to use these 2 deformations to calculate our system's deformation at a certain level. But for now, yeah, that's what happens at phase 2. And at phase 3, there is a 150% proof load that is applied and a final check done to confirm that the omega nut is still removable and thread stripping has not occurred in the rod. And of course, this is just in keeping with what AC 316 has required, as shown above in the clause 4.2.1.3. No need to memorize that. But anyway, basically what the clause says is that the device shall resist the proof load, 150% design load, 150% rod capacity, without stripping or rupture, and shall be removable from the test rod after the load is released. Yeah. So if you're wondering how we tested the omega nut to 150% capacity of the rod, we actually used a heat-treated rod that was similar in stiffness to tungsten. And even then, the omega nut didn't fail, and there was only failure of the rod. In essence, the point I'm trying to make is that our shrinkage compensating device, the omega nut, is never the failing element of the Z4 system. And this goes back to the point I was trying to make before about the simple design philosophy. So the omega net never fails before the rod, and as a result, you don't have to design your continuous rod system around the shrinkage compensating device. So what did I mean by simple design philosophy? So you simply install it without any need for future adjustments. There's only one type of shrinkage compensating device in our Z4 system, not a slew of them. It ratchets perpetually, which ensures that there is no limitation to how much shrinkage may be compensated. And as I said before, it never fails before the rod. So when it comes to specification, the omega net is really something that works in the background, leaving you to focus on what you normally would have focused on, which is the design of the rod. And I believe this is how continuous rod systems with shrinkage compensation should be. Now that we know how the omega nut works, you may be wondering about its performance under real earthquake loads. A question I often get asked is whether the omega net is going to cause the building to experience shortening as the cyclic earthquake loading changes from tension to compression. So the assumption here is that the compression part of the cycle is going to cause the structure to experience vertical compression deformation, causing the omega nut to ratchet down the rod. So once the compression swings the other way, the same thing is going to happen to the other end of the rod, and your shear wall is going to become some sort of collapsing accordion structure. I tried to animate it here, but please bear with me. So something like that. So your compression comes along, swings the other way, crushes that, swings the other way, crushes the cord on that side, and swings the other way and crushes the cord on that side. So now this seems to be what most people think happens to your timber shear walls if you have a shrinkage compensating device that's going to ratchet. So to answer this, I have two parts to my answer. So number one, I want to say that if your building does experience a huge compressive deformation, that would only be as a result of the failure of the compression post. So it has nothing to do with the tie down system. So because the engineer has the responsibility to ensure that his compression posts don't fail under compression, that's what they're there for. But yeah, if your compression posts experience some sort of plastic deformation, then the omega nut at that level would ratchet down. And the second part of my response is this: if your compression posts do exactly what they're supposed to do, and they don't fail under compression, which is fantastic, there is a softening that occurs under cyclic earthquake loading. So timber gets crushed, fasteners can get pinched, and fixings may deform. And these factors will inevitably result in softening of your shear wall frame, and the omega nut will, as a result, ratchet down the rod a little bit. And what we found is that this is a good thing. Structure softening often leads to widening hysteretic behavior, and having the omega nut compensate for this actually arrests the hysteresis loop from continued widening. So yeah, so hopefully that answers that question. So now that we've covered the meat of the presentation, let's have a quick look and take a breather by watching this full-scale 6-story cold form steel building on the world's largest outdoor shake table. So let's just have a quick look at that. Hopefully that starts playing. Okay, so now here's a full-scale 6-story cold form steel structure on a shake table over in the University of California, San Diego. Is that playing? There we go. And I believe it's the world's largest outdoor shake table, where Z4 was used as the continuous rod system. There were a total of 9 earthquake simulations over 3 weeks. The first few shakes being service level, then 50% design, then 100% design, and then what's called an MCE, which is 150% the design load. And the MCE basically stands for maximum credible earthquake. And the building was then, maybe I'll just let you watch it for a second, and then we'll catch up to it. There's no audio, if that's what you were wondering. There's just some drone footage. The building was then set on fire from within, and for the first time ever, a post-fire building was subject to earthquake loads. So as you can see there, they're setting it on fire on the inside. So after this post-fire event, the building was then shaken twice. So one of them was a service level load and one more MCE, which is 150% design load. So most importantly, if you're wondering what the heck a continuous rod system with shrinkage compensation was doing in this steel structure, stop wondering, because that there were no cinch nuts there were no omega nuts being used in this test. But funnily enough, take a look at this picture that was taken before any testing took place, showing that even steel buildings experience some settlement, meaning that shrinkage compensating devices would have been welcome in the steel structure. Settlement deflections of around 3 to 4 millimeters were found for this steel structure. And I imagine it might be obviously from elastic deformation and settlement, and definitely not creep, and definitely not shrinkage. Yeah. So here's another shot of what happened inside. So I'll try go over this kind of fast, but you can see some of the Z4 rods sitting there inside. So the earthquake hasn't started yet, obviously. So that's where the rod is. And then here we go with the earthquake. That's always fun to watch. Now, an interesting find from this investigation was that the building actually resisted collapse largely due to the continuous rod system. So there's the rod again, as you can see. So that's another positive to keep in mind, is the rods provide propping to the walls post-earthquake, preventing the walls from falling over. And that's always a bonus for people inspecting the building post-earthquake or something like that. Or yeah. So not to mention that that it has its benefits during construction as well, because the rod has been praised as being a temporary prop during construction, and that's something I don't think many people think of when they're designing a building with the system in it. Yeah. Okay, so finally, let's go over a quick example of how to specify the Z4 system using the individual data tables in the Z4 tech brochure. Note that if you were going with a capacity-based approach, you would have already applied your overstrength factor to the level tensions that you see over here. So just pretend that these two figures are already overstrengthened or over-designed or something like that. Okay, so the assumptions and demands. So the design, we're designing the Z4 tie-down system for level 2. The timber type is radiata pine. The level tension at level 2 is 25 kilonewtons. The level tension at level 3 is 20 kilonewtons. The cumulative tension. So let's first of all design the rod. So we need the cumulative tension for that. And the cumulative tension would just be the level tension at level 2 and the level tension at level 3. So you add those both up and you get 45 kilonewtons, assuming that level 3 is the highest part of the building, the highest floor. So then you just take that 45 kilonewtons and you go over to the rod table. And if you're wanting to go with a standard grade rod, because we have a standard strength, we have standard grade rod, and we have high strength rod. If you wanted to keep it standard strength, you would basically just take your 45 kilonewtons and go down the capacity table and find the capacity that is greater than 45 kilonewtons. So for a standard grade rod, the first rod that does that is a 3/4 of an inch standard grade all threaded rod, and that's about 19 millimeters in diameter. And so because we've now figured out what rod size we need, we also know what cinch nut, we also know what omega nut size accompanies this rod, and that's a CNX06, because we have rod sizes, we have omega nut sizes that match all of our rod sizes. Then we design the bearing plate washer, because we already have our rod and our omega nut. So all we have to do is design the bearing plate washer. So first we determine the level tension at level 2, which is given. So that's 25 kilonewtons. So we know the bottom plate timber species is radiata pine. And basically what we're trying to do is determine a bearing plate washer size that does not cause the bottom plate to go into bearing capacity failure. So that's essentially what you're trying to do. You're trying to get a bearing plate washer that's big enough that the bottom plate doesn't crush. So you go down so we know that our bottom plate is radiata pine. So we just we take our level tension at level 2, and we go down the radiata pine column, and we find the first bearing plate washer that gives us a bearing capacity greater than 25 kilonewtons. And in this case, that is a bearing plate washer 7, and it's yellow. So now that we've figured out what components we need, there we go. So now that we know what components we need, let's go ahead and perform a deflection calculation. So we need to determine that we have to check the Z4 tie-down system total vertical deflection at level 2. So there are 3 components to this. So we have the omega nut, the bearing plate washer, and the rod. So that's what these 3 deltas are here for. So there is, as I said before, the movement of the omega nut itself, and that can be broken up into 2 components, as I previously stated. So you have the slip of the omega nut, and you also have the tensile deformation of the omega nut under maximum loading. But because we're not working at maximum capacity, we basically just we factor it with the level tension at that level, divide by the maximum capacity of the cinch nut, apply it to the maximum deformation, apply it to and multiply it to the deformation at maximum rod capacity. And then we add that to the slip of the omega nut, and that gives us something like 1.6 millimeters. And there's no need to memorize all of this. There's guidance on how to do this calculation in the Z4 technical brochure. And all of these figures, the delta R and the delta A, so the slip and the deflection at maximum load, is given in the tech brochure, so no need to memorize that either. Then we have the crushing of the bottom plate under the bearing plate washer. So that figure we assume to be about 1 millimeter. So if you're wondering why that is, there was a test done by the American Wood Council, and what they did is they took a Douglas fir, a piece of wood, a Douglas fir piece of wood, and they impressed on it using a steel plate. And they found that at 73% bearing capacity of the Douglas fir, they achieved a perpendicular to grain crushing deformation of about 0.02 inches. And that translates to about 0.5 millimeter. And they found that at maximum bearing capacity of the Douglas fir wood, that they got about 0.04 crushing deformation. And that's about 1 millimeter deformation. So if we're conservative, we can use 1 millimeter as our crushing due to crushing of the bearing crushing of the bottom plate under the bearing plate washer. But obviously, you're not going to be designing all of your bearing plate washers to capacity. So if you want, you can reduce it a little bit using this using these bilineal graph if you really want to. But you can just be conservative and use 1 millimeter if you really want. Okay, then we have the tensile deformation of the rod itself, and that's a simple equation. I'm sure we're all familiar with this, which is just PL over AE, which is P is the design load, L is the length of the rod, A is the cross-sectional diameter, and E is the Young's modulus of the rod. Note that there is no change in the Young's modulus between the standard grade rod and the high strength variant. So both of these have the same E. Their difference is that the high strength rod has a higher ultimate tensile capacity. So the E isn't actually going to change if you go from a standard strength to a high strength. You're going to have to change the diameter or decrease the load or the length. Okay, so if you perform that calculation for our 3/4 of an inch standard strength rod, we got about 2.87 millimeters of tensile deformation in the rod. So you add those 3 figures up and you get something like 5.47 millimeters per floor for the Z4 tie-down system. So then you get that 5.47 and you plug it into your horizontal drift calculations. You're going to have to transform it a little bit because remember, this is a vertical deformation. So if you apply this to your horizontal drift calculations, you then have to see if your drift criteria is being met. And that's all there is to specification. So you go ahead and you do all of that for all of your shear walls, for all of your levels, or of course, MiTek can step in and easily do that specification for you. And what you end up with is a couple of deliverables. So on paper, you get a set of shop drawings. You get a set of shop drawings that show you the chords of all of your shear walls at every level, showing you the tie down run for each of your shear walls. So for example, you have shear wall Y2, and you can see in here what omega nut size to use, what bearing plate washer to use at that level, what rod to use, what size coupler to use, so on and so forth for each and every level. And this is of course extremely handy when you're on site inspecting, or for coordination, or even for the guy on site installing. So yeah, so that's what you end up with on paper. And what you end up with on site, the other deliverable, is that you get all your Z4 components. And they can be delivered on a level by level basis. And of course, all the rods can be cut to length as per your project requirements. And yeah, that brings me to the end of my presentation. So I guess, does anybody have any questions?
Thank you, Daniel. That was a fantastic presentation. I think you actually covered quite a large number of the questions I can see on my screen, but let's quickly work through. And yeah, thanks for the really good summary, and also showing the video and the example. It really provides a bit of an idea how the system works. So there's one of our attendees is asking if there's any redundancy, or what's the redundancy system of the continuous rod system. And following on, has there any be some progressive collapse simulated with the system in 2D or 3D? Do you have any comments on that, Daniel?
So redundancy level for this continuous rod system, I'm not 100% sure what you mean by that. So I'm assuming that the question is talking about if there is failure of this of the shrinkage compensating device. Is that what they mean, or do they mean is the entire? Do you need redundancy for the entire system? Meaning, do you need tie down? Do you need brackets to be there just in case the rod fails? But I guess to answer that question, it's kind of a tricky one. I suppose if we were just answering the shrinkage compensating device side of things, there really is no need for redundancy, because at least on MiTek's end, our tests have shown that even when you use a rod as stiff as tungsten, the cinch nut, the omega nut still doesn't fail. So really, when you use it with a high strength rod that we do provide, we can always guarantee that the rod is not going to fail before this. The rod is always going to fail before the shrinkage compensating device. So yeah, but answering your other question, has any progressive collapse simulation been done? And to be honest, no, we haven't done any progressive collapse simulation. But it may be interesting to do, actually. Maybe work up a 3D model or something just to see what happens. But yeah, thanks for that.
Thank you, Daniel. There's a question from Larry about how the force travels from the rod back into the studs, but you have quite clearly explained it in a slide later on, so I jumped that one. There's another question, which is going to be a tricky answer as well, perhaps, is would you consider the rod system a low damage system?
I want to say yes and no. Yes for the okay. So let's look at no first. No, because this goes back to a point I made previously. No, because really you've got yourself what is just a steel tie down rod, and steel tie down rods have been used extensively throughout history, and really all we're doing is allowing the steel tension rod to be used in a timber building. So that is why we've introduced a ratcheting, shrinkage compensating device. So to that end, I don't want to classify it as a low damage system, but I want to say yes, because like I said, under an earthquake, we know that your timber shear walls are going to, what's going to happen is your nails are going to pinch, and that's going to cause your hysteresis curve loop to expand over time. And having the cinch nut in there is actually going to arrest some of that, the hysteretic widening, because the cinch nut is just going to ratchet down as your stories soften. So in a sense, yes, low damage. Also yes, in the sense, also yes, low damage in the sense that the rods have been known to stop the walls from collapsing over post earthquake. So low damage in that sense as well. So yes and no. I know it's not a straightforward answer, and we like straightforward answers, but yeah, that's all I can offer you. And thanks for that question.
Daniel, if you mind, if I can add something, I think the low damage system, I think the rod system as such, being designed for overstrength, shouldn't suffer damage. If the ductility is coming from your nailed plywood, then the nail is still going to yield and have some sort of damage. So I agree with you. It's a tricky answer. I knew that.
Yeah.
I think the system as such shouldn't have damage, but the plywood wall, and you mentioned it quite clearly, will undergo some softening. So
yes,
some checks of retrofit might be required after a large earthquake event. That would be my take.
Yeah.
Another simple question here is how many rods are needed on each side, and what's the distance on each side of those rods?
It depends on you, really. How long is your shear wall? And if you're asking how many rods are needed on each side, typically you see one on each side, but there are cases where we've seen a parallel run of Z4 rods, and that is because the demand was not able to be met by a single rod. So in fact, what we needed to do is increase the number of rods to satisfy the tension demand. So in most cases, one rod per shear wall cord, and yeah, the distance depends on the length of your shear on the length of your shear wall. So yeah, thanks.
Thank you, Daniel. And following on, there's another question about, can you change the size of the rods as you go up the building height?
Absolutely. So you can. That's sort of an interesting question, but yeah, of course you can, and you, Daniel, could probably comment on that as well. So you can optimize, your rod sizes depending on the tension demands of each level. But what we have found, at least with the limited buildings that we've done here in New Zealand, is that the contractors on site actually don't like it when you give them a whole bunch of rods and say, hey, go fix this in your building. They actually prefer if you just keep it one or two sizes, because although you may optimize the rod diameters to cut down on price and optimize your design, obviously, what this is doing is it's creating more components for the contractor to deal with on site. And that actually increases the amount of time they spend organizing the rods and installing them. Rather, if you have just one rod size or two rod sizes, this is going to obviously shoot up the price of your components, but it's going to keep installation on site faster and therefore cheaper. And it is my understanding that you save more money giving the builder less to do. So hopefully that answers that part of your question.
Very, very pragmatic and practical answer. Thank you, Daniel. There's another question about if there's any test data showing the ductility and stiffness of the Z4 system.
The ductility and the stiffness of the Z4 system. So let me just read that out. So is the stiffness of the tie-down system compatible with plywood shear walls, or is it much stiffer?
Yeah.
Is the stiffness of the tie-down system compatible with plywood shear walls? Yeah, I mean, most of the buildings we've seen have been most of the buildings that are done with Z4, actually even over in the States, are plywood sheathed with our Z4 rods. So I would say, yeah, they are compatible with plywood sheathed shear walls. We don't have any test data showing ductility and stiffness of the system. I suppose with stiffness, I can refer you to our test data that we did with our shrinkage compensating devices, and it shows how much movement you get when you're applying a certain load to the omega nut. So yes, we have test data on how the system, on the stiffness of the system. I'm not quite sure about the ductility of the system. I don't think we have that test data, but I can always fish around and see if we have done something in past. So yeah, good question.
I perhaps invite the author of that question to have a look at the brand's LTF guideline, which discusses stiffness and also ductility of the system. Because my guess, I also don't know the exact meaning of the question.
Yeah.
I guess the ductility, I think, is coming from the nails, not
Correct,
of the rods in this case. And the stiffness of the rods are an integral part of the plywood stiffness. So I think it's part of the system. So as such, it definitely works together. Then another tricky question. What's the shortest building you would still recommend the Z4 system for? Would you recommend it for a 2-story residential building, for example?
Yeah. No, yeah, I would say yes, because I have seen it in 2-story structures, but it was used quite creatively. But yeah, you can. I mean, it's really, this goes back to a point that I made saying it's just a steel rod. So you can use it wherever the heck you want, really. So would I recommend it for a 2-story structure? I mean, yeah, if your demands are unable to be met by your conventional studs and brackets, then absolutely bring it on. We can, and you're running out of shear walls or something like that, then maybe going with a continuous rod system may be the right thing to do. So really what I wanted to say is, I have one more slide. 1 second. There you go. So I have one more slide. So what I wanted to say is, for everybody watching, if you just scan that QR code, it'll give you my details. And what you can do is, if you've got your 2-story structures or 3 or whatever stories you've got, send it over to me, and I'd love to help you with Z4 specification and help you out with it, even if you just had questions about it or something like that. So yeah, hopefully that answers your question, Alex.
Thank you. There's another question about, is there any design guide or manual available for download? Which would have been a question I would have asked you anyway, Daniel. So perhaps you can quickly talk about your design guideline.
Yeah, so currently we don't have any guidance on compression post design. And I think that's what the questioner is asking. I'm not sure who asked that question.
That's a generic question about any information about the Z4 system. So I'm not reading the questions in order, if you wonder.
Oh yeah, was that your question, Daniel?
No, it wasn't my question, but there's a question about a possible Z4 guideline or publication.
About compression?
In general.
Oh yeah, we have a Z4 technical brochure, if that's what you're wondering.
Yes.
I'd be happy to. Was that the question?
Yes, correct.
Yeah, absolutely. We 100% have a technical Z4 brochure where we have all the capacities of all the different components. It shows you how to specify the system using the method that I showed you, plus another method that's done using what's called a quick reference table. So, by all means, reach out to me. I could be happy to come and talk to you about it, or give you a demo on how to use it. It's not very complex. But yeah, we absolutely do have technical literature on that.
Perfect. It's probably good if that can be shared to a wider audience, and perhaps this information can be sent to the attendees of this specific webinar.
Yeah,
I'm gonna do the last 2
a
questions so that people can go back to their work. A question about the design example. Has the Pinus radiata properties you have highlighted, are these the same as the New Zealand documented one?
So sorry, Daniel, could you repeat that?
Are the Pinus radiata properties used in the design the same as the New Zealand properties 23603?
Yes, they are. So our Z4 technical brochure has been tailored using the New Zealand standards. So all of our timber species used and all the steel data, all the steel capacities that have been used are all done using the New Zealand standards and capacities. So yeah, so the radiata pine columns are all done using the New Zealand properties that you would find in 3603 or the upcoming, actually done using the upcoming 1720 actually. So yeah.
Perfect. There's another interesting question. Could these ratcheting devices be used for stacked log construction on the hurricane ties? And how much force is required to make the device actually ratchet down the rod?
Oh, that's a very interesting question. I do have a sample here with me, but I've misplaced the rod. So I just have a cinch nut, so I obviously can't do a demonstration for you. But yes, to the first part of your question, I think you're referring to like something like Lockwood Homes or something like that, where they typically employ a continuous, well, I don't know if it's continuous, but just a steel tie down rod throughout the I guess the log walls. And I think that's for shrinkage compensation essentially, and they don't really use it for earthquake purposes. I think it's for tie down purposes, as you say, as a hurricane tie. And another good question is how much force is required to make the device ratchet down the rod. Depends on the size of your shrinkage compensating devices. So the smaller ones you can just push down with your fingers, even up to a certain length you can easily just push it down with your fingers. So I don't know of the specific forces you need in order to move the shrinkage compensating devices, but not a whole lot. They move down quite easily. If you'd like, what I can do, Jaisa, is if we can get in touch and I can bring you a sample and you can have a play with it and you can figure out for yourself how much force is needed.
Perfect. Thank you, Daniel. And I'm going to ask you the last question. I'm well aware there's a couple more questions there, and what we will do, we will send these questions to Daniel, and Daniel can perhaps over the next couple of days have a look and answer them via email, if that's okay with you, Daniel. Perfect.
Yeah, absolutely.
So the last question, which is quite important, and maybe you can provide some background information, is how are these rods connected actually at the base?
Oh, fantastic question. I don't think I covered that part of it. So the rod is designed to be embedded into the foundation. So it's you have essentially a nut, a plate, a nut, and a rod going through that embedded in the concrete. So the concrete is poured over it, and you have a rod sticking up about it, and then your frame sits on top of that. So to answer your question, it's connected at the base by means of an embedded rod. So the rod is embedded into the concrete when the concrete is poured in, and that's how it's embedded, connected at the base.
Perfect.
All of this information is in the Z4 technical brochure. So I think I'll just do a mass email to all the interested attendees, and be happy to send it over.
Perfect. I think that's a very good idea. I have seen this guideline. I think it is very comprehensive and answers actually quite some of the questions in here. And I invite everyone to also have a look at the brands guideline. If you put these documents together, you essentially have covered most of your design already. Daniel, thank you so much from the TDS side for giving this very excellent webinar. I like your style. I like the slides you have shown and the example. So thanks for your time. Thanks for answering all the questions, or most of the questions as well. We will follow up on the other ones. And yeah, thanks everyone else for joining in, and looking forward to the next webinar in a month's time. So thank you everyone, and have a good afternoon. Thank you, Daniel.
Thanks everybody. Thanks, Daniel.